Okay, so the first exercise is related to a single shaft gas turbine, and in particular are given some data related to the inlet condition of the fluid, the compression ratio of the gas turbine, some efficiency, in particular isentropic efficiency of the compressor and also of the turbine. It is given also the turbine inlet temperature, or better, the combustor outlet temperature, and the pressure drop related to the combustor. Then are given some thermodynamic data related to the flue gases, so the specific heat capacity and the gamma, which is the ratio between the specific heat capacity at constant pressure and constant volume. And also for the air, given some thermodynamic properties. Finally, are given two efficiency, which are the mechanical efficiency and the electrical efficiency, which will be useful to evaluate the electric power of the gas turbine. So the first request of the problem is to evaluate, to draw the plant scheme. So a gas turbine is done by a compressor in which we fed air from the ambient. In reality, here is placed an air filter for the impurities that they cannot go into the compressor, but in this case is not adopted. So here we have air, essentially. The air is compressed and goes to a combustor, in which we fed also with fuel, essentially. Then, after the combustor, we have high temperature flue gases that are expanded in a gas turbine, which drives, firstly, the compressor. This is a shaft, so the turbine power is spark to drive the compressor, and then it is linked to an alternator, and so from here we extract the electric power. After the gas turbine, the expanded flue gases, so with a pressure in this case equal the ambient pressure, goes to the ambient. So here we have the expanded flue gases. We can add also the number. For example, here is 1 for the air, 2 for the compressed air, 3 will be the flue gases, and 4 the expanded flue gases. 4, this was the first point. So then the second point is to represent the TS diagram of the cycle. So we can draw the diagram firstly. This is the TS diagram, in which we need to first draw the isobaric line. The isobaric line are done like this in the TS diagram, and in particular we will start with two lines. This will be the pressure at the inlet, so P1, the isobaric line for equal to P1, which is the ambient pressure. Then we have a compression of the air, and we go to P2. So this is P2. We can go to P2 in two different ways, with an isentropic compression, in which the entropy generated is null, so is a vertical line. So let's do it like this. This is the isentropic compression. Or what happens in reality is that we have a real compression, so we create entropy, and so what happens, what we can draw is a line like this. So this is the real compression. So this is point 2, and this is the point 2s, because is the isentropic, is the point in which we will go if we have an isentropic compression. After that, we have a combustor, and in the problem is given that inside the combustor there is a pressure drop. So essentially, what happens is that we lost some pressure inside, and so we need to draw another line, which will be P3. And after the compressor, after the combustor, essentially, we increase the temperature because we are burning fuel with air. And we will go to a pressure which is lower with respect to P2, okay? So in this case, P2 is higher than P3. And then we expand the flue gases in the gas turbine, and we will go once again to the ambient pressure. So P1 is equal to P4, which is equal to Pamb. And also in this case, we can go to P4 or Pamb with an isentropic expansion or with a real expansion, essentially. With an isentropic expansion, we will have a vertical line, as in the case of the compressor, in which, for which we do not create any entropy, but this is what ideally happens. So this will be this is 0.3, and this will be 0.4 S. What happens in reality is that we create entropy. We will reach a higher temperature with respect to the ideal case. This is 0.4, because we expand less, okay? There are some questions about this. Okay, so this is the TS diagram and the scheme plant of the gas turbine. Then the problem asks to calculate pressure and temperature of the air at the combustor outlet. So what is important to say is that air can be treated as a perfect gas. So essentially, we make the hypothesis of ideal gas plus the hypothesis to have the CD and CP constant. So ideal gas in this case, we can write that since we have a perfect gas, the relation PV the power of gamma is equal to a constant. This is a relation that is valid for perfect gas. So having in mind this, and knowing that the beta, so the compression ratio of the cycle is given and is equal to 15, we can evaluate which is the pressure at the outlet, because we know the pressure at the inlet, which is 1 bar, and essentially is the ambient pressure, so 1 bar. And from here, we can evaluate P2. So P2 is equal to the compression ratio of the compressor times P1, so 15 bar. Then we have this relation that is valid, so we can write that P1 times the specific volume in the point number 1 at the power of gamma of the air, because we are treating in the compressor, we are treating air, is equal to P2 times, we want to essentially exploit the isentropic efficiency to derive then the outlet condition of the compressor. So we evaluate, first of all, since we have the isentropic efficiency, we evaluate the thermodynamic properties not in the point 2, number 2, because in this case we have a real expansion. So we evaluate, first of all, the condition in point 2s. So we use this formula for the point 2s. So P2 is equal to P2s. So here we can write P2 or P2s is the same. And then we multiply by the specific volume in the point number, in the point 2s. So the specific volume of the point 2s. At the power always of the same fluid, which is air. So the power of gamma air. Then, from this relation, we know that since we have an ideal gas, we can exploit also the thermodynamic law that is P per V, P times V equal to R times T. And so from here, extracting the specific volume, because we want a relation that link the pressure and the temperature, extracting from here for the specific volume for point 1 and the specific volume for the point 2s, we can write that we have to this formula, which is P1 at the power of gamma air minus 1 divided by gamma air, all divided by T1, equal to P2 at the power of gamma air minus 1 divided by gamma air, all divided by T, 2s, okay? So essentially, from here, we write this, so P1 are T1 and P2s, which is equal to P2, equal to R T2s. And from here, we find V1 and V2, we substitute it inside here, and we can arrive to this relation, okay? So, from here, we can evaluate essentially the temperature in which, in the point 2s, so in the case in which we have an ideal expansion. So T2s will be T1 times P1 divided P2. So, sorry, P2 divided P1 at the power of gamma air minus 1 divided by gamma air. Okay. So we have all the data to solve this, and so we can find that T2s, so the temperature at the end of an ideal expansion, ideal compression is 616.03 Kelvin. Then, what we want to know is the real temperature, so the exit of the real compression. And find it, we can exploit the definition of isentropic efficiency. So the isentropic efficiency of the compressor is defined as the ratio between the ideal work of the compressor, so in case of an ideal compression, divided by the real work that we have. So will be M of the air times Cp of the air times T2s minus T1 divided the mass flow rate of the air times Cp of the air times T2 minus T1. So this is the real work which is higher with respect to the ideal one. And so the mass flow rate of the air in these two cases is the same also for the constant, the specific capacity. So what remains is T2S minus T1 divided T2 minus T1. And reversing this formula, we can find T2, which comes equal to, so I write here, T2 will be equal to T1 plus T2S minus T1 divided the isentropic efficiency of the compressor, and it comes equal to 673.89 Kelvin. Be careful to use in this formula the correct unit of measure, which is Kelvin. There are questions about this? Okay. Then it is asked to calculate pressure and temperature of flue gases at the turbine outlet. Okay, so after the compressor, we will have the combustor in which we increase the temperature, and essentially we have also a pressure drop in the combustor. So the pressure drop is equal to 3%, and so we can write that, so delta P over the inlet pressure at the combustor is equal to, this is the same to write P2 minus P3 divided P2 is equal to 3% essentially. Okay, so we can write that in P3 the pressure will be equal to P2 times 1 minus the relative pressure drop, which is equal to 3%, so delta P over P2, and this comes equal to 14.55 bar. So essentially, we have a relative pressure drop with respect to the inlet pressure of 3%, so we will have at the outlet 97% of the inlet pressure. That is, at the inlet we will have 15 bar, so at the exit of the combustor we will have 14.55 bar. Concerning instead the pressure at the outlet of the turbine, in P4, as I said before, P4 will be equal to 1 bar because we will have the same inlet of P1, so this is 1 bar. So I write here, P4 will be equal to 1 bar. Essentially, we need to use the same relation that we use for the compressor, so evaluate firstly the point for S, so at the end of an ideal expansion, and then through the definition of isentropic efficiency of the turbine, we can evaluate the temperature in point 4. So, as before, we can write that T for S over T3, which is this relation, over T3 is equal to P4 over P3, because in the point number 4S, the pressure is the same as in the point number 4, so here we can avoid S, okay? At the power of gamma. In this case, we do not have any more air, but we are expanding flue gases, so we need to use the correct gamma. So gamma of the flue gases minus 1, all divided by gamma of the flue gases. From here, we can evaluate T4S, which comes equal to 755.15 and 25.15 Kelvin. Once again, with the definition of isentropic efficiency, so we can derive T4. So the definition of the isentropic efficiency for the turbine is the real work, so the real expansion over the ideal one. In the ideal case, we expand more, so M of the flue gases times the Cp of the flue gases times T3 minus T4 divided, this is the real work in the real expansion, divided M of the flue gases times Cp of the flue gases times T3 minus T4S. And in this case, from here we have everything. The only unknown is T4, and from here we can evaluate T4, which comes equal to 785 Kelvin. There are questions? T3 is given. Yeah, is 1,200 degrees Celsius. So the last point is related to calculate the net electric power output of the gas turbine. And so to do that, we will do a power balance. So we can write that the power output, the net electric power output of the turbine will be, say right here, gas turbine, will be the power output of the turbine minus the power output of the compressor, all multiplied by the mechanical efficiency and the electrical efficiency, which are given. So let's calculate before the power output of the turbine. So P out of the turbine is equal to the mass flow rate of the flue gases times the Cp of the flue gases times T3 minus T4, and it comes equal to 75.697 megawatt, while the power output of the compressor is the same, but it elaborates a mass flow rate which is lower because it's just the mass flow rate of the air, and the Cp that we need to use is the one related to the air, and the temperature will be T2 minus T1. So P out of the compressor is P in. Okay, so P in of the compressor is mass flow rate of the air times Cp of the air times T2 minus T1, and in this case it is equal to 38.559 megawatt. So using these two values inside this formula, we can, and multiply by the mechanical efficiency and the electrical efficiency, we can arrive to the net electric power output of the gas turbine, which is equal to 36.216 megawatt. Okay. Okay, this is the first exercise. This was the first exercise. Do you have any question about this exercise? Okay.
You consider the fuel gases to be helper gas also, with the constant CP, or?
No, it is given just that at the exit of the turbine, at the exit of the combustor is given all, and you consider the flue gases as an ideal. Okay. So the fuel is not important in this case. Yeah, flue gases are ideal gases. Okay. The second. Okay. The second exercise instead is related to both a steam turbine and an hydraulic pump, for which we cannot consider the assumption of ideal gas. So let's start from the steam turbine expansion. So given the following two transformations, determine the outlet temperatures using the steam tables or the Mollier chart, which are given in the exercise text, exercise lesson test. And so let's start from the steam turbine expansion. Once again, we will have a plant like this. So the scheme is we will have an inlet stream. So this is exercise number 2. An inlet stream, which is steam, essentially, at a certain temperature, T1, which is equal to 550 degrees Celsius, at a certain pressure, P1 equal to 128.8 bar. And after the expansion in the steam turbine, we will have the flux number 2 with P2 equal to 42 bar. And it is given the, so here we will have a certain power output. And it is given the isentropic efficiency of the turbine, which I reported here, equal to 0.87. So in this case, differently from the previous exercise, we cannot consider anymore the assumption of ideal gas. And so we have to use the, for what concerns water, Mollier chart and the tables that are given also as PDF in the course section dedicated, and in particular, to the Mollier chart we have to derive the other thermodynamic properties related to the stream, which are essentially the enthalpy and the entropy. For a superheated steam, and only in the case instead of a fluid which is in transition of phase, we need one properties. Instead, for superheated steam, we need two properties to define the other. In this case, so since at the inlet of the steam turbine we will have two properties, temperature and pressure, we can derive all the other thermodynamic properties. So in point number 1, thanks to the temperature at the inlet, which is given, and the pressure of the inlet, so this is P1 and this is T1, through the Mollier chart or through the steam tables, we can derive the enthalpy at the inlet. So HIN equal H1 equal to 3,472.63 kilojoule per kilogram. Obviously, if you use the module chart, you cannot be precise like this, but in this case, I use a software to have this value. And we can derive also the entropy at the inlet, so S in, which is equal to S1, which is equal to 6.61 kilojoule per kilogram Kelvin. Then, as we have done before, we consider, since we have the isentropic efficiency of the turbine, firstly we consider an isentropic expansion. And then, thanks to the definition of the isentropic expansion, we can derive all the other properties in point 2. So, let's write here. So, firstly, considering isentropic expansion. Isentropic expansion. We can write that S2 will be equal to S1. S2 in point 2S. So it's something like, as done before, we will have a certain, this is the DHS diagram. So for water is something like this. We are in a point like this one. TS diagram, let's do. This is P1. If we and this is, for example, P2. If we consider an isentropic expansion, we have a vertical line, and this will be point 2S. In a real expansion, we will have something like this. Yeah, like this. Okay, so we consider now the point essentially 2S, and we say that the entropy in the point 2S, since it's at the end of an ideal expansion, will be equal to the entropy in point number 1. Another thermodynamic property that we have in point 2S is the pressure, because the pressure is equal between point 2S and point 2. So here we know the pressure of the point 2S, which will be equal to the pressure of the point 2, and so equal to 42 bar. Once again, we have two properties, and entering in the module chart with these two quantities, we can derive the other. We can derive that the vapor fraction is equal to 1, so we have all vapor, all steam, and superheated steam essentially, and we can derive H2S equal to 3,125.32 kilojoule per kilogram, and also the temperature at the outlet of the isentropic expansion, so T2S, equal 364.69 degrees Celsius. Then, as we have done before, using the definition of isentropic efficiency, we can derive the temperature in the point number 2 in the real expansion. So, the isentropic efficiency of the turbine in this case is defined as m of steam entering the steam turbine times the enthalpy at the inlet. So H1 minus, we need to use the enthalpies in this case instead of Cp times T, because we are not considering anymore an ideal gas. Okay, so for steam, we cannot use the assumption of an ideal gas, so we need to use the enthalpy. Okay? And so H1 minus H2, which is the real expansion, obviously, also in this case, lower than the ideal one, which is m dot of the steam, so the mass flow rate of steam, times H1 minus H2S. So the enthalpy that we have evaluated considering an ideal expansion. In this case, so the mass flow rate of steam is the same, and the only unknown is H2. So from here we can evaluate H2, which comes equal to 3,170.47 kilojoule per kilogram. Now, in point number 2, you know the enthalpy and the pressure. So for point are known H2 and the pressure. And once again, with the Moglia chart, you can derive the other properties, and in particular the temperature, which comes equal to 383.17 Kelvin. Sorry, this is in Kelvin, not degrees Celsius. So what you can notice is that this temperature is higher than the ideal one because we are expanding less the fluid. So you can notice also here this thing. So the temperature that you have at the end of the real expansion is higher since you are expanding less the fluid and you are extracting less power. Okay. There are some questions about the steam turbine. Okay. So the other request is related to an hydraulic pump, and in particular also in this case we have to evaluate the outlet temperature, and it is given the temperature at the inlet, the pressure at the inlet, and it is given that we have saturated liquid, the pressure at the outlet of the pump, and once again, the hydraulic efficiency of the pump. So for the pump, we make the hypothesis of uncompressible fluid. And in particular, we can write two relations, one for the enthalpy difference, so delta H equal to CL times the temperature difference plus the specific volume of the fluid times the pressure difference. And this value will be constant since we consider the fluid elaborated by the pump as an uncompressible fluid, so the heat density does not change, and so since the specific volume is the inverse of the density, also the specific volume does not change. And we can write also the relation for delta S, which will be equal to also in this case a function of temperature, so CL times the logarithm of T over T ref. If we consider an ideal case, what happens is that, so the delta S, as in the case we have seen before, will be equal to 0. That means that the temperature does not change along the compression of the liquid in the pump. So we can say that if we consider the objective is always to consider firstly an ideal, let's say, an ideal compression of the fluid, and then with the hydraulic efficiency evaluate real thermodynamic properties of the cycle at the outlet of the pump. So if we consider an ideal case in which delta S will be equal to 0, we can say that also the delta T will be equal to 0, okay, from here. And considering the delta H, which is essentially the work of the pump, in an ideal case, so delta H ideal will be equal to just V plus V times the difference in the pressure. Now, take in mind these things. At the inlet of the pump, what you know, so in the inlet section, what you know is the pressure, which is given, and the temperature, so P1 and T1. And it is given that the condition of the fluid is saturated liquid. So it is given also that P, which is the steam quality, is equal to 0. From the tables, you can derive the other properties, as we have done before. So you can derive that H1 will be equal to 670.42 kilojoule per kilogram, and that the specific volume of the fluid is equal to 0.0011 cubic meter divided kilogram. Okay. Then, given this value, considering the fact that you are making the hypothesis of uncompressible fluid, so V will be constant, you can evaluate the ideal work, because this will be also the ideal, let's say the ideal work. Delta H ideal is equal to the ideal work, and will be equal to V1 that you know, and the difference in the pressure. The pressure at the outlet is given, is equal to 175 bar. So the ideal work, let's write here, the ideal work will be equal to V in times P out minus P in, and it comes equal to 18,590 kilojoule per kilogram. Okay, it's clear. Then, as we have done for the steam turbine and before for the gas turbine, we use the definition of an efficiency, in this case the hydraulic efficiency, to evaluate the condition in the real compression. So let's write here. You know which is the hydraulic efficiency of the pump, which is given, and its definition is equal to the ideal work divided by the real work. So, which will be equal to the ideal work divided, yes, H. This is the specific work, so H out in the real case minus H in. So, the ideal work, you have evaluated the ideal work before, the hydraulic efficiency of the pump is given, the enthalpy at the inlet, you can evaluate it thanks to the thermodynamic properties given at the inlet. And so, the only unknown in this case is the enthalpy that you have at the outlet in the real compression. So, H out, which will be equal to 693.66 kilojoule per kilogram. These, so you have the enthalpy at the outlet in the real case and the enthalpy in the inlet, knowing that the real work can be written like this, so as a function of temperature and pressure, so Cl times delta T plus the specific volume times delta P, we can write that H out minus H in will be equal to Cl times delta T, in which you have T2 minus, so T out minus T in, plus the specific volume which remains constant, so you can use V in, times P out minus P in. In this case, for Cl you can use the value of 4,186 joule per kilogram Kelvin. And so the only unknown in this case is the temperature at the outlet. So reversing this formula, you can evaluate the out, which is the request of the problem, which comes equal to 160 degrees. It's clear? Okay. Okay, no questions about this exercise? Okay. Oh. Okay, let's start the other exercise and then we can have a break. So let's read together the text. So in a food industry, this is an exercise related to a shell into heat exchanger. So you have to do a design and then the off design of the heat exchanger. So in a food industry, a shell into heat exchanger featuring a counterflow configuration transfers heat from a stream of diathermic oil, which is flowing inside the shell, to a stream of water, which instead is flowing within the tubes. In nominal condition, the water mass flow rate is equal to 300 kilograms per second, and is heated from 20 to 80 degrees. Whereas the oil enters the heat exchangers at 170 degrees Celsius and exits at 40 degrees. The transfer coefficient and nominal operating condition on the water side is equal to 1000 watt per square meter Kelvin, referred to the internal diameter of the tubes, while the sum of the conductive resistance of the tubes and the convective resistance of the oil is an even value. The first question is related to the design, and it is required to evaluate the heat exchanger area referred to the internal diameter of the tubes and the effectiveness in nominal condition. So let's write before the data and also the scheme of the heat exchanger. So exercise number 3, we have an heat exchanger which can be schematized like this. So we will have this is the oil which is entered with a certain temperature that we can call T in oil. Then we have the heat exchanger section, and it exits with a certain temperature. So this is the oil side, and then because it is given that is a counterflow configuration, so the water goes in the other direction, we will have this will be T in of the water. And this will be T out of the water. We can call the two sides of the heat exchanger also as side A and side B. Okay. The data are the mass flow rate of water, which is equal to 300 kilograms per second. Then we have the temperature at the inlet of the water, which is equal to 20. The temperature at the outlet of always on the water side, which is equal to 80 degrees Celsius. The temperature at the inlet of the oil equal to 170 degrees Celsius, and also at the outlet equal to 40 degrees Celsius. And then we have the heat transfer coefficient of the water, so we can call it HI equal to 1000 watt square meter Kelvin. and the resistance of the total resistance of the conductive resistance of the tube and the conductive resistance of the oil is given directly the sum of the two, so we can call it RT plus O equal to 3.904 times 10 at the power of minus 7 watt over Kelvin. For solving the point number 1, related to the design of the heat exchanger, it is useful firstly to draw the TQ diagram of the heat exchanger. So, okay, so this is side B, while this one we can call it side A of the heat exchanger. We will have the oil that enters with a certain temperature, T oil, and is cooled down up to the temperature T out of the oil. On the other side, the water enters with a temperature equal to T in of the water, and it is heated up to a certain temperature, which is T out of the water. This is the TQ diagram, and so you have everything for evaluating the heat exchange inside the heat exchanger. So, which is equal to Q dot equal to, you can choose one of the two sides, and not in this case, you have to use the side of the water because you have the mass flow rate of the water. So Q dot is equal to M, mass flow rate of the water, times Cp of the water times T out of the water minus T in of the water. You have everything. This is always 4,186. And so you can evaluate the power exchange, the thermal power exchange, which comes equal to 75,348 kilowatt. Now, this is the first way to write the relation for the thermal power exchange inside an heat exchanger. You have always another way, which is related to the geometrical characteristic of the heat exchanger. So you can write that Q dot is also equal to the global transfer coefficient times the area at which the global transfer coefficient is referred, times the mean logarithmic temperature difference of the heat exchanger, which is delta T ml. Why? So it is important always to link, in this case, U times A must be always linked to a certain area. So this is valid if you use, for example, the global transfer coefficient referred to the external area times the external area times delta T ml. But this is also equal to Ui times Ai, which is the internal area of the heat exchanger, and the global transfer coefficients related to the internal area of the heat exchanger times delta T ml. So be careful when you use this formula to use the global heat transfer coefficient and the error corrected. In our case, we have a suggestion because it is given that the transfer coefficient for the water is on the internal area, is referred to the internal area. So what we can evaluate is essentially the product between UI and AI, which with the electric analogy is equal to 1 divided the total resistance. Let me draw a scheme. So you have, this is a tube in which the water flows, and essentially this is the thickness of the tubes, and essentially starting from the center you have 3 different resistance to the heat flux. The first resistance is related to the convective resistance between the water and the internal side of the tube, that we can call Ri. Then you have a conductive resistance due to the material of the tube that we can call Rc. And then, since at the external side of the tubes is flowing oil, essentially you have a convective resistance once again on the other side that we can call R oil. Okay. In the text, what is given is that this sum of these 2 resistances is equal to a certain value. And it is a data of the problem. So H, what we have called here, RT plus RO. So let's call here T instead of C. So this will be RT plus O. While for this case, in this case, the resistance associated to the convective the convective resistance between the water and the internal side of the tubes is equal to Ri and is equal to, from theory, 1 divided, let's write not here, Ri. So this will be the total resistance, and Ri will be equal to 1 divided Hi times Ai. Okay? So, since UA times AA is equal to the inverse of the total resistance, we can write that this is equal to 1, these are resistance in series, in which we have 1 divided Hi times Ai plus RT plus O. Okay? So essentially you can rewrite the thermal power using the global heat transfer coefficient referred to the internal area and the times the internal area times the mean logarithmic temperature difference. So Q will be equal to, as we have said before, UA times AA times delta T ml, which is equal also to 1 divided 1 divided hi times ai plus rt plus o times the delta t ml. All this value, so Q is known, hi is known, and also the value of the total resistance of the conductive resistance and the convective resistance on the outside. What is missing is this area, and it is also what we want to evaluate. But we miss also the mean logarithmic temperature difference. The delta TML can be evaluated as the delta T on the side A minus the delta T that we have on the side B of the heat exchanger, all divided by the logarithm between the delta T on the side A divided the delta T on the side B of the heat exchanger. So, in other words, this is equal to T in oil minus T in oil minus T out water minus T out of the oil minus T in of the water, all divided by the logarithm of T in of the oil minus T out of the water, all divided T out of the oil minus T in of the water. And this is equal to, you have all the values, and this is equal to 45.54 Kelvin. Now, using this relation, you can reverse it, exploiting the thermal power that you have evaluated here, the value that you have for Hi and RT plus O, and the value that you evaluated for the mean logarithmic temperature difference. You can evaluate the only unknown, which is Ai, which comes equal to 4,400 square meter. Then the other request of the problem is to evaluate the effectiveness of the heat exchanger in nominal condition. Concerning the area of the heat exchanger, there are some questions. Okay, so let's evaluate just the effectiveness of the heat exchanger, and then we can have a break. So the effectiveness of the heat exchanger is defined. Can I withdraw this part? Yes. Okay, the effectiveness of the heat exchanger is expressed as the thermal power divided what is called Q infinite, which is thermal power exchange in the case in which we have an area of the heat exchanger which is infinite. This is the definition of Q infinite, okay? So, how is defined Q infinite? In other words, is equal to So the heat capacity lower between that we have lower between the two fluids times the temperature at the inlet of the hot fluid minus the temperature at the inlet of the cold fluid. This is the minimum heat capacity that we have between the two fluids. This M times C of the fluid for what concerns water and for what concerns oil. We need to evaluate which is the lower one and use inside this formula. So in this case, we can have two cases. Let's write them here. Okay. The case A is the one in which we have the heat capacity of the hot flow of the fluid lower than that of the cold fluid. The case B instead is the inverse, so C hot greater than C cold. For these cases, we can also write the TQ diagram, and in particular, okay, so considering case A, we have a TQ diagram that is done like this. So the hot fluid has a slope higher with respect to the cold fluid. So this is the hot fluid, while this one is the cold fluid. Okay, so this is T in hot, T out hot, T in cold, let me write here, T in cold, and T out cold. Okay, so this is the real thermal power exchange, what we call Q, in the form of the effectiveness. In the case of C hot lower than C cold, Q infinite will be equal to this. So if we have essentially an area that is infinite, we can bring the temperature of the hot fluid equal to the temperature of the inlet fluid on the cold side. So this essentially would be Q infinite. Okay. In the other case, instead, is the opposite. So we have a hot fluid like this. A hot fluid that cools down less than the heat up of the cold fluid, okay? So this slope, in this case, is higher for the cold fluid. So this is, once again, hot fluid, and this is the cold one. T out hot, T in cold. And once again, in this case, with an infinite area, we reach the condition in which the cold fluid reaches the temperature, so this point, reaches the temperature of the hot fluid at the inlet. So this will be Q infinite, while this one will be Q, okay? This is the real temperature of the cold fluid at the outlet, and this is the inlet temperature of the hot fluid, okay? So in this case, we have that Q, which is equal, we can write it in terms of both the cold fluids and the hot fluids, so will be equal to C of the water, the heat capacity of the water, which is essentially the heat capacity is the product between the mass flow rate of the water times the Cp of the water, times the delta T on the water side, but could be written also in terms of the heat capacity of the oil, so C of the oil, times the delta T on the oil side. Then, since the thermal power is the same, and you know which is the temperature difference on the oil side and on the water side, you have that this is equal to 60 degrees Celsius, and this is equal to 130 degrees Celsius. From here, you can derive that we are in a case equal to A, and so that C oil is lower, so the heat capacity of the hot fluid is lower than the heat capacity of the water, which is the heat capacity of the cold fluid, okay?
Can you repeat why you understand that?
Okay, because you know that Q is the same, and you can write heat in terms of both heat capacity of the oil times delta T of the oil, and heat capacity of water times the delta T of water. Since the delta T of the water is lower, the heat capacity of the oil will be lower to expect the same thermal power. Okay, so in this case we have a higher delta T, so the heat capacity of the oil must be lower to have the same heat. Instead, in this case, 60 times something higher could respect the thermal power, okay? From always here, you can evaluate which is the value of C oil. So from here, it's reversing Q in divided by delta T of the oil is equal to C oil. And then, using this formula, you can evaluate Q infinite. So even using this one, you know that C min is the one of the oil. So you can evaluate Q infinite as C oil times T in hot minus T in cold. And then you can evaluate the effectiveness of the heat exchanger because Q is known from before, 7 25,348 kilowatt. You have evaluated Q infinite, and so you can evaluate the effectiveness of the heat exchanger at nominal condition. Let's call it epsilon nom, which comes equal to 0.866 and so on. Okay, so this was the first part of the third exercise, and now we can have a break of about 15 minutes up to 16, okay? Okay, so the second part of the third exercise is related instead to the off design of the heat exchanger. We can read together the text. So suppose that due to an increase in the demand, the plant should operate at twice the nominal production, and it is therefore required to heat from 20 to 80 degrees Celsius, which are the same temperature as the one at nominal condition, at double mass flow rate of water, with the same oil mass flow rate. The request is assuming that the overall heat transfer coefficient does not change. It is required to determine inlet and outlet temperatures of the oil, exploiting this relation, which linked essentially the epsilon, the NTU, and the CR for a counter flow heat exchanger. Okay, so let's rewrite essentially which are the data of the problem of design condition. We know that the mass flow rate of the water is double, so it's 600 kilograms per second. We know that we want to increase the temperature, heat up from 20 to 80 degrees Celsius as a nominal condition, so these two remain the same. We want to evaluate which are the new temperature for what considering the oil. We can assume essentially, since we can assume that the overall heat transfer coefficients remain the same, we can assume that since the area of the heat exchanger is the same because it's the same heat exchanger, also these two remain the same since the global heat transfer coefficient remain the same, okay? So we can leave it. And what we know is that the mass flow rate of the oil is constant and is equal to the mass flow rate of the oil that we have at nominal condition, okay? So, moreover, it's given a relation that link together the effectiveness of the heat exchanger with the NTU and the CR. The equation that is given essentially could be given as an equation as in this case, or could be given also with some graphs. Yeah. Sorry. Yeah. Okay. Thank you. So, the graphs are done like this. So, maybe you have seen them in theory. So you have the epsilon related to the NTU and different curves for different CR, where this is the orientation of an increasing CR. Then, what are NTU? NTU is the number of transfer unit, so NTU, and it is the ratio between the global heat transfer coefficient times the area, always referred to the same area, so global heat transfer coefficient, in our case we talk of UI times AI, divided C min, so the heat capacity of the fluid, the lower heat capacity of the fluid, while CR is the ratio between C min and C max. Okay? So, in off design condition, in this case, what we can say for sure is that the thermal power is doubled, because Q can be written as m of the water times the CL of the water times the delta T of the water. So could be m in off-design condition times CP, CL, C of the water, which is 4,186, and the delta T of the water. Since the delta T in off-design condition remain the same, and the mass flow rate of the water in off-design condition double is 2 times, so the mass flow rate of water in nominal condition, we can for sure say that the thermal power will be 2 times the nominal power. So this is the, so the nominal power is Q norm will be equal to m water at nominal condition times CL times delta T at nominal condition of the water and the off designing is the same. So we can assume, we can say for sure that Q in the off design condition will be equal to 2 times the thermal power at nominal condition. So we can write that is equal to 150,696 kilowatt. Then we need to reasoning about the heat capacity and define which is the minimum heat capacity between the two fluids. And as in the previous case, we can for sure say that C min is heat capacity of the oil. Why? Because we have that the heat capacity of the oil remains the same, because the mass flow rate of the oil is the same. While, for sure, the heat capacity of the water increases. And since before C oil was lower than C water, also in this case we can assume for sure that C oil will be the lower one between the two. Okay, so this is equal to M oil times CL of the oil. Okay. Previously, we do not evaluate it, C oil, so we can do now. So C oil can be evaluated as Q divided T in of the oil at nominal condition, because you know that the mass flow rate of the oil remains the same between off design and design, and the heat capacity, the specific heat capacity of the oil is the same. So we can use, so the heat capacity, so the multiplication between M oil and C oil is the heat capacity, can be evaluated at nominal condition. So we can use the thermal power divided the difference at nominal condition. Obviously, this you have here you have to use the nominal condition. So T in oil at nominal condition minus T out oil at nominal condition, and this comes equal to 579.6 kilowatt over Kelvin. It's clear, while we evaluated C oil thanks to the nominal condition. Okay, so now essentially with evaluating sea oil and knowing that it remains the same, and knowing that is the minimum one, so this is also C min, we need to evaluate the heat capacity of the water, which is the maximum one, to then evaluate the ratio between the two, and so CR. So how we can evaluate it is just the mass flow rate of the water times CL of the water. And it comes equal to 2,511.6 kilowatt over Kelvin. Now, what you can do is also calculate the ratio between the two. So CR, which is C min over C max, is equal to 0.2308. So essentially, what happens is that C max, C min between the design case and the off-design case remain the same. C max increases, and so CR decreases with respect to the nominal case. We do not evaluate before CR, but if you want to evaluate, you will see that CR in the nominal condition will be higher with respect to the off-design condition. However, in the form, it's clear. Okay, so, however, in the equation that is given for the effectiveness, because we want to evaluate the effectiveness, the new temperature of the oil, we need to evaluate also NTU. NTU is the definition of the NTU is given here. So in this case, we can say that NTU will be equal to UI times AI divided C min. Now, for what concern this value, since the heat transfer coefficient remain the same, and also the resistance related to the conductive resistance and convection resistance on the oil side remain the same, we can say that in off-design condition, UA remain the same. Okay? The global heat transfer coefficient remain the same. The heat transfer, the heat exchanger is the same, so the area is the same. And as I said before, the C min, which is the heat capacity of the oil, remain the same. So we can say that the NTU in off-design condition will be equal to the NTU at nominal condition. And so, exploiting the definition of thermal power as a function of UA times the mean logarithmic temperature difference, we can evaluate the UA at nominal condition. So we can say also is C min at nominal condition. So to evaluate UA at nominal condition, we can write that UI times AI at nominal condition will be equal to the thermal power at nominal condition divided the mean logarithmic temperature difference at nominal condition, which are all values that we evaluated before. And so we can evaluate the product between UI and AI at nominal condition, which comes equal to 1,619 kilowatt over Kelvin. Now, you have evaluated UA times AI, and you can so evaluate the NTU, which remains equal between nominal condition and of design condition. So you can evaluate NTU, which comes equal to, so using, let's say, this value inside here, and Chimin, which is the heat capacity of the oil, you can evaluate the NTU, which comes equal to 2.793. So then, exploiting the formula, which is given in the text, you can derive which is the new effectiveness of the heat exchanger, which is equal to 0. So exploiting the formula, I write here the value, the new value. Epsilon in off design condition is equal to 0.908, and you can notice that with respect to the value that we have evaluated before is greater. Because essentially for the same NTU, so we can suppose to be here in a nominal condition, for the same NTU which remain the same, we have a CR that is lower because we are increasing the Cmax, and so we will find essentially this was the nominal condition, decreasing CR, we will find an effectiveness which is higher than the nominal one, okay? This is the off design condition. Let's say off design number 1. Because now we will see another condition. It's clear? Okay. So, the other condition is repeat the previous calculation, taking into account the variation of the overall heat transfer coefficient originated by the variation of the water velocity flowing within the tubes. Sorry. The exercise, the point is not finished because it asks to evaluate the temperature. So we need to evaluate the temperature. So before going on, we can evaluate the temperature through energy balances. So the temperature of the oil. And so with the new effectiveness, you know, the definition of the effectiveness is Q over Q infinite. And so from here, you can evaluate the new thermal power exchange. So Q will be equal to epsilon in off design condition, let's say of design number 1, times Q infinite. Where Q infinite remain the same because this is also equal to epsilon in off design condition number 1 times Cmin, which is, as before, the heat capacity of the oil, times the temperature of the oil at the inlet minus the temperature of the water at the inlet. So Q, we have evaluated before, that is 2 times the nominal one. So this is 2 times the nominal one, because the mass flow rate of water doubled. So what remains as unknown in this equation is the temperature at the inlet of the oil. So we can evaluate it, which comes, the equation, reversing the equation is T in oil equal to T in of the water plus Q in off design condition divided by epsilon times C min, where this is Q. And so from here we evaluate a temperature of the oil at the inlet, which is 306.41 degrees Celsius, greater with respect to the previous one, which was 170. And so then, exploiting an energy balance, we can evaluate also the temperature of the oil at the outlet. So writing that Q dot is equal to the heat capacity of the oil times T in of the oil minus T out of the oil. And this comes equal, the only unknown in this case is this one, so the temperature of the oil at the outlet, and so we can derive this value, which comes equal to 46.41 degrees Celsius. Okay, so the oil, since it has to be guarantee a higher thermal demand, and so it has to heat up more the mass flow rate of water that is double, needs to enter, since the mass flow rate of remain the same, needs to enter with a higher temperature, and it exits with a temperature which is similar to the previous one, which was 40. And this is due also to the increased effectiveness of the heat exchanger. Then we can proceed with the third question related to the so repeat the previous calculation, taking into account the variation of the overall heat transfer coefficient originated by the variation of the water velocity flowing within the tubes. The convective heat transfer coefficient between water and tubes wall can be estimated by means of the Ditus-Bolter equation, which is given in the text, also with the parameters of n and okay. Then is given that Nusselt's and Reynolds numbers are referred to the internal diameter of the tubes, and it is given that to solve the exercise, neglect the variation of the thermophysical properties, viscosity, thermal conductivity, and specific heat of water with the temperature. Okay, so in this case we are talking about another off-design condition in which we cannot anymore consider that UE remain the same because we have a variation in the heat transfer coefficient of the water due to the change in velocity inside the tube. And so we can write that sorry. So we have, now we are facing the off design, say 2, and so HI changes with the velocity, so it's a function of the velocity. The Ditus-Bolter equation given in the text is Nusselt's, referred to the internal diameter of the tubes, is equal to 0.023 times the Reynolds number. These are empirical correlation, okay, at the power of 4 divided by 5 times the Prandtl number at the power of 0.4. Okay, I write here the definition of Nusselts, Reynolds, and Prandtl. So Nusselts is equal to the heat transfer coefficient times the diameter, internal diameter of the tubes divided by the thermal conductivity of the fluid. Reynolds is rho, so the density times the velocity times the diameter divided by mu, so the viscosity. And Prandtl instead is equal to mu times Cp times divided by K. So these are the definition of the adimensional number which characterize the empirical correlation. And in particular, what we can write is that, so is that the Vitus-Bolter equation can be rewritten in this way. So we have, in the off-design condition, number 2, we have that the Nusselts, which is equal to H times D divided by K, is equal to 0.023 times the Reynolds number, so rho times V times D divided by mu at the power of 4 divided by 5 times mu times Cp divided by K at the power of 0.4. Essentially, just rewrite the Vitus-Bolter equation expliciting the dimensional number. Why I've done this? Because I want to highlight which are the parameters which remains equal between the off-design condition and the nominal condition. In particular, the diameter of the tubes is the same. Then is given that the thermo-physical properties remain the same. So essentially, we can consider that for the Nusselt numbers, this part remain the same. For the Reynolds number, between the nominal and off-design condition, these parts remain the same. And also, all the Prandtl number remain the same. So these remain constant between the correlation that we use in off-design condition and the correlation that we use in nominal condition that I can write here. So we can H D divided K. This is nominal condition. At nominal condition is equal to 0.023 times rho V divided by mu at nominal condition at the power of 4 divided by 5 times mu times Cp divided by K at the power of 0.4 at nominal condition. So, dividing the two equations, 1 and 2, you obtain that H divided by velocity at the power of 4 divided by 5. In off-design condition, this is the condition of design. Is equal to H divided by the velocity at the power of 4 divided by 5 at nominal condition. Okay? So, we can rewrite also in this way. H divided by H nom equal to V divided by V nom. Okay, so now we need to understand which is the new value of H, or better, to understand which is this ratio, we need to understand which is the ratio between the velocity in off-design condition and the velocity at nominal condition. Since the mass flow rate of the water is equal to ρ times the velocity of the water times the area, the cross-sectional area of the tube, this is AT, let's say. These between nominal case and off-design case remain the same. And we have said that the thermophysical properties of the fluid remain the same, so also this part. But we know that the mass flow rate of water between the nominal case and the off-design case doubled. So what we can say for sure is that since the mass flow rate of the water is double, also the velocity in off-design condition is 2 times the velocity at nominal condition, okay? It's clear? So, from this equation, we can, so using this this relation inside here, we can derive the new value of H, which comes equal to H at nominal condition times essentially V over V nom is equal to 2, so 2 at the power of 4 divided by 5. This is the ratio between V and V nom. And so we can write that this is equal to 1,741 watt per square meter Kelvin. What is important to say is that the heat transfer coefficient increases with the velocity, okay? Also, thanks to the, we can see also from here, in which on the left you have the heat transfer coefficient, which is directly proportional to the velocity, which is contained inside the Reynolds number. So if you increase the Reynolds number, you increase essentially the heat transfer coefficients of the fluid. So it is better to have a fluid that goes with a high velocity to transfer heat, okay? So now you have the new HI, so the new heat transfer coefficient, and so you can evaluate UI times AI, as we have done before. So UA times AI is equal to 1 divided 1 HI, in this case, the one that we have calculated now, so the one associated to the off-design 2 times AI plus RT plus O, which remain the same. This comes equal to 1,919.64 kilowatt over Kelvin. And so we can compute the new NTU, because the NTU, we know that is equal to UIAI divided C mean. The C mean is the same. The new NTU increases because ui times I is greater. Okay. And this comes equal to 3.312. CR is the same, is Cmin over Cmax, and is the same. So 0.2 is the same as in the of design 1, so 0.2308. So with the formula, you can evaluate the new effectiveness, which is 0.939. 0.939. So what happens is that in this case, you have the same CR, so you are in this condition. You have done nominal condition of design number 1, but the of design number 1 and the nominal condition has the same NTU. In this case, you move across the same CR, so across this curve, and you obtain a higher effectiveness because you obtain a higher NTU. Okay, this is the NTU in of design 2. Okay, it's clear? Then, also in this case, we have to evaluate temperature, exploiting, I don't have anymore here the three heat balance that I've written before, but exploiting the same procedure that you have that we use for the of design number 1, we can evaluate which are the temperature for the T oil at the inlet, which comes equal to 296.98 degrees Celsius, and then with this you can evaluate also T out of the oil, which comes equal to 336.98 degrees Celsius. So for this point, you have to evaluate, you have to use the same balance equation that we used before, but the important is more related to this. Okay, so once again, the effectiveness of the heat exchanger increases because the number of transfer units increases with the same CR. It's clear? Okay, so we can proceed with the last exercise. I think I will go up to, I hope in half an hour. So let's start. Do you want to have another break before starting this one? Or okay, okay, okay. So the last exercise is related essentially to a reactor, in particular water gas shift reactor, in which we have at the inlet. I could withdraw. Okay. In which at the inlet we have a certain molar flow rate of a gas composed by CO, so carbon monoxide, and steam. Then we have this reactor which has a catalyst inside, which favorites essentially the reaction to form as product CO2 and hydrogen. Okay, the water gas shift reactor is done to increase the hydrogen content on molar basis into the exiting stream from the reactor. Okay, so for solving the problem, so the reactor is given the molar flow rate at the inlet, so I read the text. So the reactor is alimented by 200 kilomole hour of gas, whose composition is reported in the table. The reactor temperature is 500 degrees Celsius and operates at 1 atmosphere. It is said that we can neglect the kinetic and potential energy differences between the inlet and the outlet streams, and then are given the standard enthalpy of formation, the minute capacity of the species, the low rating value, and the molar mass. Then the problem is split in two parts. One considering a conversion of the carbon monoxide equal to 100%, and then the problem is to repeat essentially the point from point 1 to point 3 with a conversion efficiency which is lower. Okay, so in this case, also in this case, we can draw a scheme, and so for the reactor is more theoretical, this exercise, than practical, say for the exam. But so you have, this is which the chemical reactor, which is isothermal and isobaric, which is fed with a gas composed by CO plus water in form of vapor, and inside there are the water gas shift reaction, and so at the exit we will have CO2 plus H2. Okay, so the data that we have are the molar composition, so molar composition. In particular, we have 50% of CO and 50% of water in form of vapor. So here we have 200 kilomole per hour entering. Since we have some heat entering that favor the reaction, and that is used essentially to break the bonds between the atoms, and then at the exit always 200 kilomole hour. Then what we know is essentially the molar composition, so 50% of CO at the inlet and 50% of H2O. And then are given also the enthalpy of formation, the minute capacity for all the different species. What you have seen during the lecture is that essentially to understand which is the value of this heat, you have to do an energy balance on the reactor, which involves the total enthalpy of the fluid of the fluids at the inlet and at the outlet. The total enthalpy of a fluid, okay, let's start and then I will define the total enthalpy. So, point number one asks to, first of all, calculate, so considering a conversion of, let's report here, a conversion of 100%. So all the CO reacts with the water, giving CO2 and hydrogen. The first question is calculate the outlet molar flow rate in kilomole per hour of each species. So since the water gas shift reaction is CO plus H2O, that gives CO2 plus H2, you can see that for 1 mole of CO2, it is needed 1 mole of water for having 1 mole of CO2 and 1 mole of hydrogen. This means that if you have a inlet flows of 200 kmol/h of CO and H2O. So this mixture, in which essentially you have 50% of CO and 50% of H2O. At the inlet, you will have essentially, so the inlet stream that we can call S1, for example, S1 is equal to 200 kmol/h. But since you know that you have 50% of CO and 50% of water, you have 100 kmol/h of CO entering and 100 kmol/h of hydrogen of water entering. Then, since the conversion is in the first part of the problem equal to 100%, and you know that for 1 mole of CO that reacts with 1 mole of water, you have 1 mole of CO2 and 1 mole of H2, you can for sure say that at the exit, the stream number, this is, let's say, S2, the composition, the molar flow rate of the stream S2 will be 100 kmol/h of CO2 and 100 kmol/h of hydrogen. Okay? It's clear? Then it asks to determine the molar composition, the mass flow rate, and the mass composition of the outlet stream. So for what concerns the molar mass of the outlet stream, so S2, it's simply at the exit, since we have that all the CO reacts with water. At the exit, we will have only CO2 and hydrogen, and so we can say that for sure CO as the molar percentage of CO is equal to 0. That it's X is equal to 0%. The same for what concerns the water. While the molar percentage of the CO2 will be given by the ratio between 100 kmol, so the molar flow rate, let's say the molar flow rate of the CO2 at the outlet divided the total molar flow rate, so N dot, which is equal to 100 kmol/h of CO2 divided 200 kmol/h, and this comes equal to 50%. Okay, it's simply the same for the hydrogen. So will be equal to N of hydrogen divided by N dot, and so it comes equal to 50%. Okay, this is always, you have 100 kmol/s of hydrogen divided 200, and so this is equal to. Okay, so then for what concerns the mass flow rates of the species, you have just to multiply by the molar mass of the molar flow rate. To pass from molar flow rate to molar mass, you can just multiply by the so the mass flow rate. You have to just to multiply by the molar mass. So m, for example, of let's say, okay, for sure, M of CO and M of H2O will be equal to 0 kilogram hour, okay? And then the mass flow rate of the CO2 will be equal to the molar flow rate, so N of CO2 times the molar mass of the CO2. And this comes equal to 4,401 kilogram hour. And the same for what concerns the mass flow rate of hydrogen. So will be equal to N hydrogen times M of the hydrogen, and this comes equal to 201.6 kilogram hour. Then, if you want to evaluate the mass composition of the stream S2, so mass composition of S2, you have just to use these two values divided by, so the mass fraction of the CO2 will be equal to the mass flow rate of CO2 exiting divided by the total mass flow rate exiting, where the total mass flow rate exiting is the sum of these two. So m dot will be equal to the sum of the mass flow rate of the species exiting by the reactor. So in this case, you obtain 95.62, and the epsilon of H2 will be equal to m dot H2 divided by m dot. And so it comes equal to 4.38%. Obviously, for the CO and for the water, the mass fraction will be equal to 0%. Okay. Now, the third point of the problem asks to evaluate the heat released by the reactor. So this heat, and to do that, we need to write an energy balance, in particular on the species entering and on the species exiting. So, since we are considering, let's say right here, as you have seen also during the lecture, an ideal mixture of ideal gas, we can use the summary of the species entering plus this heat and pose them equal to the power related to the sum of the species exiting. So it's more simple to write it. So writing the energy balance. We can write, since we consider an ideal mixture of ideal gas, we can write that NCO times the total enthalpy of CO entry of the CO plus the mass flow, the molar flow rate of the water entering times the total enthalpy of the water. On molar basis, this sign is to indicate that is a molar basis. But you can do same on mass basis, okay? Of H2O plus Q dot in is equal to N of CO2 times H dot of CO2 on molar basis, yes, plus N H2 times the total enthalpy of the hydrogen. Okay, so this can be done since we are considering an ideal mixture of ideal gas, and in particular, since we are considering an ideal mixture of ideal gas, the total enthalpy is not function of the partial pressure of the species component the stream. So you can write essentially that, let's say, with the hypothesis, with the hypothesis of ideal mixture of ideal gas, we can write that the n of a certain stream, for example S1, and this is valid always, is equal to the sum, times the total enthalpy of this stream will be equal to the sum of the various molar flow rate times the total enthalpy associated to the species. And also that, this is valid always, and also that H, this is the important thing, H dot I, so the total enthalpy of the species I, is equal to the enthalpy of formation, so delta H Fi, always on molar basis, plus Cp mean, so a mean specific heat capacity on molar basis of the substances I, times the temperature at which the reactor is minus a reference temperature. If you are not considering an ideal, so if you're not considering an ideal gas, you cannot write Cp times T minus T ref. And moreover, if you are not considering an ideal mixture, you cannot write these just in terms of temperature, but you have to write also in terms of pressure, partial pressure. So you have to do these hypotheses, okay? Okay, now I think also that during the lectures, we have seen that this is a chemical approach. Otherwise, you can use also an engineering approach, which instead of the enthalpy of formation of the various species, uses the low rating value of the various species. So this can be written, so this is chemical approach. While the engineering approach is the same, but it uses the LHV. Okay, so now turning back to the exercise, what we have to write is that we can evaluate the, first of all, the total enthalpy for all the various species composing the energy balance, so H.CO, H.8, H2O, and so on. So let's write. It's clear up to now. One more thing about the total enthalpy. In reality, what you have for a total enthalpy of a certain species, for example, H dot I is in reality, for example, considering the chemical approach, will be delta H F I plus the kinetic energy of the fluid I plus the potential energy, so G Z, times Zi, plus what is called plus yes, H I, okay? So the enthalpy. These two values, we have neglected these two values because essentially you can understand that between this flux and this flux, the kinetic energy remain the same. So if you add, for example, the kinetic energy for the stream entering, then it will be avoided by, let's say, the difference. Then you have to do the difference between the inlet flows and the outlet flows, and the kinetic energy, since is the same, they lead one each other. So I don't write here the kinetic energy because it leads when you do the difference between what is entering minus what is exiting, okay? Or better, what is exiting minus what is entering. And the same for the potential energy. Okay, so this was a parenthesis. So let's evaluate the total enthalpy for the different species. So considering, for example, CO, we can have that the total enthalpy of CO is equal to the enthalpy of formation given by the text plus Cp times the temperature of the reactor minus Tref. And this, for example, is equal to minus 110.53 kilojoule over mole plus 30.6169 divided by 1000 to have the correct unit of measure times 500 minus 25, and this comes equal to minus 95.98695 kilojoule over mole. You have not to be precise like this, I just report the value that I have here. And then you can do the same for all the other species, okay? So you have for the H2O, you have the total enthalpy of H2O is equal to delta H plus Cp times T minus Tref, and this comes equal to minus 224.391775 kilojoule over mole. And do the same for, I don't write anymore, the formula is always the same, just changing these. And so for what concerns CO2, we will have that the total enthalpy is minus 370.8392 kilojoule over mole. And instead, for what concern the hydrogen, we will have that the enthalpy of formation for the pure species with a chemical approach is 0. So you will have that delta H will be 0, and you will have only the contribute due to the enthalpy of the fluid. So it comes equal to H2 13.9327 kilojoule over mole. Okay. It's clear up to now. Okay, then solving the energy balance, you can find Q in. So Q in Q in will be equal to NCO2 times H dot CO2 plus etc. So by reverting just the energy balance, you obtain a value equal to minus 365.2780 kilojoule hour. So then dividing by 360 to have this in kilowatt, you obtain a thermal power which is equal to minus, you can see also here, minus 1014.66 kilowatt. This minus means that the reaction that is taking place inside the reactor is an isothermic reaction, okay? Otherwise, it was an endothermic reaction if the sign was positive. Okay, I just say something about the other approach. So essentially, if you use the same approach, so you write the energy balance, but instead of evaluating the enthalpy, the total enthalpy of the species with the enthalpy of formation, you use the LHV, the results that comes out is more or less the same. It's difficult to have just the same value because find the low rating value that has the same approximation of the enthalpy of formation is different. So maybe there are some differences. But for example, in this case, if you evaluate the Q with an engineering approach, it comes equal to minus 1010.33. Okay, this difference of 4 kilowatt is due to approximation. Okay, but my suggestion is to use my suggestion is to use the chemical approach. Okay. Then you have to do essentially the same for the case in which a conversion of the CO, the conversion of the CO is lower and equal to 85%. So without writing everything again, can I withdraw this part? No? Okay, so so what you obtain in case you have conversion efficiency lower than 100%, that is what happened in reality, because at this temperature, in a water gas shift reactor at 500 degrees Celsius, you don't reach the 100% of conversion. But in reality, we obtain more or less 60% of conversion. So the chemical equilibrium is a condition in which you have a conversion efficiency of 60%. Now, the problem gives a conversion efficiency of 85%. In this case, at the outlet, you don't obtain only anymore CO2 and hydrogen, but you obtain also some CO that is unconverted and don't react with water, and some water that is no use for the reaction of water gas shift. So essentially, what is important to say is that since only 85% of CO, so let's rewrite the CO plus H2O gives CO2 plus hydrogen. Since you have at the inlet always 200 kilomoles hours of this gas. And from the water gas shift reactor, you know that for the reaction of the CO2, we need 1 mole of water that creates 1 mole of CO2 and 1 mole of hydrogen. Essentially, what you obtain at the exit, since only of the 100 kilomole hour that you have before, since only 85% reacts, at the exit, what you obtain is a composition in which you have 15 kilomole hour of CO and 15 kilomole hour of H2O that are not reacts. So let's say S1, which is the inlet stream, is always 200 kilomole hour. And since the molar composition is always 50% CO and 50% water, you have 100 kilomole hour of CO and 100 kilomole hour of H2O. Since the conversion is just 85%, of these 100 kilomole hour, only 85 kilomole hour reacts. So and create 85 kilomole hour of CO2. So at the exit, you will have 85 kilomole hour. So this is S2 stream, kilomole hour of CO2. 85, because you create also one, if the CO reacts, create 1 mole of H2, 85 kilomole hour of H2. And since the sum must always 200 kilomole hour, you know that 15 kilomole hour will be of CO that do not react, and 15 kilomole hour of water. It's clear? Then, as we have done before, we can evaluate the molar composition of the flow, the mass flow rate of the various species, and the mass fraction. And I just report here some of the values. So, for example, I report here. We will have that in this case, molar fraction, we will have XCO equal to 7.5%, X of H2O will be equal to 7.5%. This is evaluated always as N of the CO divided N tot. X of CO2 is equal to 42.5%, and X of H2 is equal to 42%. Okay, then we have to do the same. Okay, you have to do the same for the mass fraction of the species. So the mass fraction of the species mass fraction, that's mass flow rate, sorry, the mass flow rate of the species exiting is just m of the species I is equal to n I times mmi. Be careful that in this case you have a mass flow rate of also CO and water exiting because you are not converting all the CO. Then you can evaluate the mass fraction as n epsilon I, so the mass fraction of the species I equal to m I divided m tot, where m tot is the sum of the different mass flow rate of the different species. And finally, what is really important is to write the energy balance once again. So the energy balance in this case, do not consider, in the energy balance we have to consider also the fact that the CO is not reacted, not the CO reacts, so we will have that on molar basis the energy balance is n CO times the total enthalpy on molar basis of the CO plus n of H2O times the total enthalpy of the water. These, let's write in because they are the molar flow rate of the species entering, so in H2O plus Q in equal to what? To N CO2 times the total enthalpy of CO2 plus N H2 times the total enthalpy of H2 plus N CO out, meaning that we have some mass flow rate, molar flow rate of CO that is exiting because not only is converted into CO2 and hydrogen, times the total enthalpy of the CO, which is the same because the enthalpy of formation is the same, and the temperature of the reactor between inlet and outlet is the same because it's isothermal, and plus the molar flow rate of water unreacted, so out, let's say, times the total enthalpy, once again, of the water, which is equal to the inlet one, so the total enthalpy does not change. Once again, you can evaluate the total enthalpy as we have done before, so the total enthalpy, neglecting the kinetic and potential terms of the I species, is equal to the enthalpy of formation of the species I plus Cp min times T of the reactor minus Tref, where essentially Tref is 25 degrees Celsius. And then you can evaluate essentially the power, the thermal power requested in this case, released in this case, which comes equal to, I write here the results, so Q in, if you solve it, it comes equal to minus 862.1718, let's say, kilowatt. And you can notice that the power output of the exothermic reaction reduces, since we have a lower conversion of the CO, so we need to break lower bonds, chemical bonds in the between the atoms. Okay. Okay, that's all. Sorry to be in delay. And if you have any question, I'm here up to 18. Okay, let's close. And now I want just